Okay, so good afternoon once again. In the last lecture, we discussed that if Y is a subspace of topological space X, then what is the meaning of the cover of Y by the subsets of X? So the collection A alpha of subsets of X will cover Y. That means every element of Y, I can find one A alpha such that that element belongs to A alpha. So in other words, Y is a subset of union of A alpha, and here we are considering the cover of the subspace Y. Therefore, we are taking the subset, and otherwise, if we are considering the cover of the topological space X, then we discuss. Hello, am I audible?
Yes, sir, audible.
Okay, so if X is a X is a topological space, then the cover means X is exactly union of A alpha, right? So this is the difference between cover of the subspace and cover of the space X. That the cover of the subspace we take the subset relation, and the cover of uh, the topological space we take equality here. So this is meaning of the open the cover of the subspace, and for the open cover, this is the criteria that if Y is a subspace of a topological space X, then Y is compact with respect to the subspace topology. If and only if we have a cover of Y by open subsets of X.
Sir, you are not audible.
So what about others? Am I audible?
Yes, sir, you are audible.
Yes, sir.
So because it is from your side, and I cannot help for that actually. So you can reconnect otherwise. Okay, so let me continue that if we have the open cover of the subsets of X of Y, then this cover has a finite subcover, right? So this property we have called it is a star property, and this is basically the criteria which is equivalent to the subspace is a compact space. And as an application in the last lecture, we proved that every closed subset of a compact space is compact, right? So what does it means mathematically is that if Y be a closed subset of a topological space capital X, then Y is always compact space. So this is the result regarding when the closed subset becomes compact. So if that closed subset is a subset of compact space, then it will automatically be a compact space. And what about the converse, that when the compact space becomes closed? So for that we have discussed this result that every compact subset of a Hausdorff space is always closed. So Hausdorff space, we know there are several examples. So one such example is a real line with the standard topology, and R cross R with the standard topology. That is the XY plane with the standard topology. So this result says that every compact subset of the Hausdorff space, so in particular every compact subset of R is closed, right? So if I have a compact subset of real line, it is always closed. So what this result, the application of this result is that if I have any subset of the real line which is not closed, then it cannot be compact space, right? So for example, open interval if I take, which is a subset of real line which is not closed, so open set is not compact using this theorem. So this is one of the application, and so And the last result which we discuss is that we proved that connectedness is a homomorph is a topological property. So that means it is preserved under continuous function. So this result says that compactness is a topological property. So if I take a image of a compact space, it is also a compact space. A continuous image of a compact space is always compact space. So that means if f is a function from x to y which is continuous, and if we know x, capital X is compact, then fx is also compact. And if f is a bijection and f inverse both are continuous, that means f is a homomorphism, then x and y are homomorphic. And if x and y are homomorphic, then if x or y, any of them is compact, then the other space will be compact. Using this theorem, we can prove that easily, because homomorphism means f and f inverse both are continuous. So that is a stronger condition. So compactness also is preserved under the continuous functions. It is a topological property. So this is what we discussed in the last lecture. Today we want to discuss some more examples of complex spaces, and for that what we want to prove is if X is a compact topological space and Y is also compact topological space, then X cross Y is also compact space. So that is similar to the result which we proved for connected spaces, that if X and Y both are connected, then X cross Y with respect to product topology is connected. So to prove that result, we need a special lemma which is known as tube lemma that we want to prove today. But before that, I want to discuss one example regarding the complex spaces. So let us start with that example. Okay, so so I'm starting with a non-empty set X with the cofinite topology. So we know that cofinite topology means any subset U of X is open with respect to the cofinite topology if complement of U is a finite set, right? So that idea basically we want to use here. So now yes. Any doubt? So what we want to discuss is that if X is any non-empty set, that means there are two cases. One case is that either X is a finite set or X is a infinite set. So first case we want to discuss is that X is a finite set, and in this case, if we take an open cover of the set X, then basically we want to prove that X is a compact space. That means whatever open cover I take, I can always find its finite subcover, which contains all points of the set capital X. So let us start with an arbitrary open cover of capital X, and on X we have cofinite topology. So that will give us U alpha is open. That means X minus U alpha is a finite set. Right? X minus U alpha is either a finite set or it is whole of X. So there are two conditions. So so now so we are starting with open cover of x1 x2 xn. X1 x2 xn are the elements of capital X, and we want to find U alphas which contains all these elements basically. And if I can find only finitely many u alphas which cover all these elements, then we are done. So since this set is finite x1 x2 xn, we can actually randomly choose u alphas which one by one covers this set. So for example, for x1 I'm finding one u alpha which contains x1, that u alpha I will call u alpha 1. For x2 I will find u alpha, that corresponding u alpha I will call u alpha 2. Similarly for xk I will get u alpha k which have the point xk inside u alpha, right? Because x is a subset of union u alpha, every element of x should be in at least one u alpha. That u alpha I will call u alpha k, which covers xk for every k belongs to 1 2 up to n. So now for every xk I got u alpha k which is open, and xk belongs to u alpha k. So that means union of xk is subset of u alpha k. And we know that this is the set x, the whole set x, because x is a finite set having this x1 x2 xn elements. And on the other hand, what we are getting is a finite union, and each u alpha k is a subset of x. So therefore union u alpha k is a subset of x. So therefore what we get is x is exactly this set, union of u alpha k. And this sets u1 u alpha 1 u alpha 2 and u alpha k is a finite set. All right, so basically this is a finite set of open sets which covers the entire space x. So therefore it is a finite subcover of u alpha. So starting with any cover u alpha, we have found a finite subcover by selecting open set one by one which contains the points one by one. And if you note that we have not, in the selection of u alpha k, we have not used the topology, right? We have just selected u alphas based on the points which we are selecting. So there is no role of topology in this first case when x is a finite set, because as many elements we have, we can choose as many u alphas which contains those points one by one. So therefore whenever x is a finite set, whatever topology you can consider on that particular set x, that is always a compact space, right? Every finite set is a compact space with respect to whatever topology you choose on that set. So that is case 1. Now case 2 is regarding the special topology, cofinite topology, we will actually use in case 2. So what is case 2? Case 2 is that x is an infinite set. So infinite means it can be countably infinite, it can be uncountably infinite also. So in this case, again, we want to show that x is compact with respect to the cofinite topology. And therefore, once again, we will start with an open cover of x, where these open sets are open with respect to the cofinite topology. Right? So what it gives is that we will have at least one v beta such that x minus v beta is not x, right? So an open subset of x means either the complement is finite set or it is whole of x. If it is whole of x, that means v beta is null set, because x minus v beta is x. So we will choose a non-empty set v beta, so that I can always choose because x is covered by union u beta, right? So and x is a non-empty set, so therefore there exists at least one v beta which is a non-empty set. So since x is non-empty set and v beta is open cover of x, I can choose v beta naught so that beta naught is not equal to x. So therefore x minus this open set is not x. So that means it is a finite set, right? Because in the cofinite topology, a set is open if there are two things: either the complement is finite set or it is the entire space. So here, because v beta naught is non-empty, it is not entire space, so therefore it is a finite set. So this particular v beta naught does not contain all the points of x, but it contains all but finitely many points. So that means x minus v beta naught is y1, y2, ym. So these are the only finitely many points which are not in v beta naught, but they are present in x. So what this gives is basically we have x which is a union of, so from this we get x is a union of v beta naught with the this particular elements which are not in v beta naught. So now the same trick of case 1 we will use here, because now we have finitely many points y1, y2, ym, which one by one we can choose from the one by one open sets. So for y1 we will choose v beta 1, y2 we will choose v beta 2, and ym we will choose v beta m. So that way we'll get finitely many open sets v beta 1, v beta 2, v beta m, which covers this set, and along with this another open set it will cover the entire space x. So x is union of v beta naught with y1, y2, ym, and y1 belongs to v beta 1, y2 belongs to v beta 2, and ym belongs to v beta m. So therefore this set is a subset of this set, and every open set v beta is a subset of x. So therefore we get this relation, and x is a subset of this set which is subset of x. Therefore this set is exactly x, right? A is a subset of b is a subset of a, then a is equal to b. So what we proved is that we have written x as a union of finitely many open sets from the collection v beta, and this is possible for every collection v beta which we choose, which covers the space x. So whatever open cover v beta of x you give, I will choose a finite subcover in this way which covers the entire space x from that cover. So that therefore we have verified the definition of the compactness. So in this case, when in the second case when x is infinite, also we can choose a finite subcover, therefore x is compact with respect to cofinite topology. So whatever set x we take, whether it is finite or infinite, and uh, we give we define cofinite topology on that particular set x, then with respect to cofinite topology x is always a compact space. So this is a simple example which we have discussed. So now let us move to the tube lemma. So tube lemma is a fundamental result that gives that consider the product space X cross Y. So we know that the X cross Y has the product topology on which we have basic open sets which are of the form U cross V, where U is open in X and V is open in Y. So with respect to this particular product topology, we are selecting a point P in X and assume that the space Y is compact in the X cross Y. So using this assumption, if we take any open subset W of U cross Y, which is open with respect to the product topology, and it satisfies this property that singleton P cross Y is a subset of W, then we can find an open set U of X such that U cross Y is a subset of W. So what is this set singleton P cross Y? If you recall, then this set singleton P cross Y means basically we are fixing X equal to P, and X equal to P in R2 is nothing but the vertical line. Alright, so if I have a kind of vertical line is subset of W, then I can find a subset U on X axis that U cross Y is subset of W whenever Y is compact. So Y is compact means Y is basically closed interval if we are taking in Y equal to the Y axis. So we want to prove this result using basically set theory, because now X and Y are topological spaces. So we start with a particular element of Y. So let Q be a element of capital Y, and we know that we have already fixed the element P of X, right? So P is a given element of X. So if I fix an element Q of Y, then P comma Q is in P cross Y because P belongs to X, and P cross Y is subset of W, that is given in the hypothesis. P cross Y is a subset of W. So we have an open set which satisfies this property that P cross Y is subset of W. So that is given. And PQ is belongs to this set, so PQ belongs to W. And also it is given that W is an open set. So open means open with respect to the product topology. So now PQ is an element of W and W is open set in X cross Y. Now we can use the definition of open subset of the topology generated by basis. So if I have any point X in an open set U, then I can find a basis element such that X belongs to be contained in U. And if I consider the product topology, then the basis elements are of the form U cross V. So this U is basically different from this U, right? So all the elements are of the form U dash cross V dash, and U dash is open subset of X and V dash is open subset of Y. So using this property we get, since PQ belongs to W, we can always find UQ cross VQ, which is a basic open set in X cross Y, such that PQ belongs to this set which is contained in W, right, where UQ is open in X and VQ is open in Y. So here I could have denoted UQ by UP also because it contains P, but I have not done that because the choice of UQ and PQ is coming from this particular point Q. which we have fixed, right? So if I change q one by one, I will get a pair u comma v here, one by one, depending on which q I am taking. So therefore I am denoting u and v by uq and vq corresponding to whatever q given. So therefore every point p comma q in w, I will get the pair uq cross vq. So that vq belongs to uq cross vq, which is subset of w. So in particular for every q, I am getting vq. So every q I am getting vq, which is open subset of y. For every q belongs to y. So now I can take union of singleton q, that is y, and that is contained in union of vq over q belongs to y. So what I got is basically I got a open cover of the topological space y, and what is given in the hypothesis is that the topological space y is compact space. So by the definition of compact space, if I take any open cover of y, then I will always get a finite subcover, right? So if I choose, if I take any open cover vq of so this is a particular open cover vq of which is open cover of y, then since y is compact, so vq is open cover of y and y is compact, I will get a finite subcover vq1, say vq1, vq2, vqn of y. So now basically we got y is a union of vqi, I running from 1 to n, and corresponding to this vq1, vq2, vqn, we have also sets uq1, uq2, uqn. So that is coming because of our choice, that whenever I have vq, I have also uq, corresponding uq, and those uq1, uq2, uqn, I am taking their intersection. So what are these uq's? Uq's are open subsets of x, and I'm taking intersection of these sets, which I am calling the set u, and since each of these sets are open subsets of x, the intersection u is also open subset of x, and it contains the point p. Why it contains the point p? Because p belongs to uq for every q, right? Because p is a fixed point, we are only changing q, p is a fixed point. So p is a fixed point that is given in the statement, that is element of x. So p belongs to each uq, therefore it is in the intersection of uq, therefore p belongs to u. So now what we get here is that since u is an open subset of x, why u is open subset? Because u is a intersection of uq, and each uq is open in x, so therefore u is an open subset of x. So therefore u cross y is open in x cross y. In fact, it is a basic open set in x cross y, right? Because what are the basic open set in x cross y? They are of this form, right? U cross u dash cross v dash, where u dash is open in x, v dash is open in y. So u cross v is a basic open subset of x cross y in the product topology. So therefore it is open, and the last thing which we want to prove is that u cross y is subset of w. So what is w? W is the, let us go to the statement. W is the open subset of x cross y which contains p cross y. And what we want to prove is that there is open set u so that u cross y is a subset of w. So what is this u that we already found? That u is the intersection of uq1, uq2 and uqn. So u we have already found. So only thing we need to check is that u cross y is a subset of w. So open set we already found. So that is our claim that u cross y is a subset of w that we want to prove. And so basically we are proving one set is a subset of other set. So what we will show is every element of the first set belongs to the second set. So if A is a subset of B, if we want to prove, then we will prove that every element of A belongs to B. So let us start with the element of the first set. XY belongs to U cross Y. So that will give us that X belongs to the first set and Y belongs to second set. And then we know that Y has a subcover. V1, VQ1, VQ2, VQn. Right? So Y can be written as a union of VQs, VQ1, VQ2, VQn. And Y is a small y is element of capital Y. So therefore Y belongs to some of the VQIs. That particular QI I will denote by I naught. So therefore Y belongs to VQ I naught, where I naught is belongs to 1, 2 up to n. Right? So we got Y belongs to VQ where Q is QI naught, and we know that corresponding to each VQ there is a UQ. So that particular UQ we can choose. So this particular Y belongs to VQ naught. What about X? So that X we know that X is an element of U. X is an element of U, and U is the intersection of UQ1, UQ2, UQn. So therefore X belongs to each of these set because it is in the intersection. So X belongs to UQ1, UQ2, UQn, and QI naught is one of these QIs, right? Because I naught is either 1, 2 or n. So therefore X belongs to UQ I naught. So in between you can write that because X is in UI for all I belongs to 1, 2 up to n. So since X belongs to each UQI, it also belongs to UQI naught in particular. And once we get this, we can finally write X comma Y belongs to UQI cross VQI, because X is in UQI and Y is in VQI. Right, so X cross Y belongs to UQI naught cross VQI naught, and every such pair UQ cross VQ is already in W. So let us recall how we define UQ and VQ. So each for given Q, UQ cross PQ is always subset of W for every Q. So therefore, for Q naught also, Qi naught also, UQ naught cross VQ naught is a subset of W. Right? So here we can write because UQ cross VQ is subset of W for all Q. So therefore, this set is a subset of W, and XY belongs to this set. That means XY belongs to W. So we started with the element X comma Y, which is a what was our claim? Our claim is that we started with any element xy in U cross Y, and we wanted to prove xy belongs to W. So that is what we proved here, that xy belongs to W. Therefore, the claim we have proved, and that will prove this particular lemma, which is known as the tube lemma. So let us once again go through the statement, what we have proved. So if we consider the product topology on X cross Y, where X and Y are topological spaces, and if I take any point P in the first space capital X, and we assume that Y is compact, and if we take a open set W of X cross Y, and which contains the line X equal to P, so basically singleton P cross Y, then there exists an open set U of X such that U cross Y is subset of W. So in fact, singleton P cross capital Y is not a vertical line, because Y is a compact subset, and therefore in real line it will be a closed interval. So P cross Y will be kind of a line segment. Singleton P cross closed interval. So it is a line segment, vertical line segment. Okay, so I think this is enough for today.